Okay, so for today, we are talking about ellipses defined parametrically. And this is going to be a little bit of well, it is definitely an application. It's kind of an out there application, no pun intended. Um, but hopefully it'll be something that might be a little bit more interesting than just looking at equations and talking about a particle that's moving. So you all know the planetary orbits. We can talk about how these planets are orbiting using parametric equations. And as we kind of start to think about how we can talk about them, first thing to know is that they are not, well, so first, planets orbit the sun due to gravitational force. And the other thing to know is that these orbits are not perfect circles, but they're actually ellipses, right? So it's not that we on Earth, as we rotate around the sun, it's not a perfect circle, but it's an ellipse, right? So we reviewed ellipses a little bit, how we have what's called a kind of a quote unquote vertical radius versus a horizontal radius. It's kind of stretched out more in one direction than the other. So a couple of astronomy definitions just to get us acquainted with some terminology. So the distance that a planet is from the sun at any given time is measured in astronomical units, or AU. And one astronomical unit is equal to 93 million miles, or 149.6 million kilometers. This is the average distance from the Earth to the sun. So yes, we kind of make everything around us, even though everything is revolving around the sun in our solar system. But the average distance from the Earth to the sun is 1 astronomical unit. Okay, so you can see this is in astronomical units for each of the planets. We'll talk about Pluto in a little bit. A couple other astronomical definitions. An aphelion is the point on the orbit of a planet where the planet is furthest from the sun. Okay. Next is the perihelion, which is the point on the orbit where the planet is closest to the sun. So if you're starting to think about the ellipses and where that planet would be in its orbit, so you're thinking about where it is farthest from the sun, where it's closest to the sun. Okay, and then the orbital period is the time in Earth years that a planet takes to complete one orbit around the sun. And then the last definition that we'll talk about is what's called eccentricity. So when we talk about eccentricity, we're talking about a measure of how much the orbit deviates from a circle. Okay, so the eccentricity of an orbit is a measure of how much the orbit deviates from a circle. So eccentricity is given as a value e between 0 and 10. So something with eccentricity of 0 deviates very little from a circle, whereas 10 is very eccentric, right? Okay, so a circle has eccentricity equals 0. The closer the value of e is to 0, the more circular the orbit appears. So here you can see the eccentricity of each planet's orbits. So you can see Mercury has a much higher eccentricity than Venus, right? Those are probably very drastically different. And Pluto has an even more eccentric orbit than Mercury. Okay, but also notice that if you look on the y-axis here, the eccentricities, even though eccentricity is given as a value between 0 and 10, you can see that the eccentricities are all here under 1. So they're fairly close to being a circle, but they're not exactly circular. Okay, so what about Pluto? So Pluto has a very different orbit than the other planets. It is far more eccentric, as we saw on that graph before. And it is tilted at a 17-degree angle from the plane in which the other planets' orbits lie. Here's actually a picture if you want to kind of have a better idea of just how all the planets are orbiting. And you can see Pluto's is the one that's in yellow here. And so if you look at it here we go. So if you look at it from this point of view, you can see how it's tilted, unlike the rest of the planets. So Pluto's unusual orbit can actually cause it to be closer to the Earth than Neptune. This happens every 248 years. The last time it happened was February 7th, 1979 until February 11th, 1999. Okay, so that's kind of a fun fact for you. Now, because of the tilt in Pluto's orbit, although their paths look like they touch, the two planets won't actually collide with each other. But what if we use our imaginations a bit and pretend that they actually do lie in the same plane? Then, boom, the two planets would actually collide. So let's mess with the universe a little bit, because we can with math. And we'll make some assumptions in order to create a universe where Neptune and Pluto could crash. So we'll assume that the planets revolve on the same plane, so it's a two-dimensional plane. And at time t equals 0, Pluto and Neptune are aligned with the Sun at their perihelions. And we're going to, for the sake of what we're doing, ignore the physical size of the planet. Okay, so obviously planets have a certain size, and that will obviously affect them crashing. But we're going to think about each planet as just a point. All right, now for planetary orbits, we can model their orbits as an ellipse with this rectangular equation that you should be familiar with from Algebra 2. So we have x minus h squared over a squared plus y minus k squared over b squared equals 1. So h comma k is going to be the center of the ellipse. A is the length of the horizontal quote-unquote radius, and b is the length of the vertical quote-unquote radius. Now, the issue with using this is that it is not enough for us to describe planetary orbit, right? With planetary orbit, we want to be able to talk about the direction, right? So this only gives the paths of the planets. But if we want to be able to give direction, we can use parametric equations so we can locate the planet in both space and time, right? So parametric equations, it's in terms of a parameter t, so at a certain parameter t, time t, we can locate where the planet will be. We can say x equals this, y equals this at a certain time. Okay, so the parametric equations which model an ellipse, well, x equals a cosine of wt, y equals b times sine of wt. Now you might recognize this as a problem that we did in a previous lesson where we converted from one form to the other, and I said, oh, remember this? This is actually just the equation of ellipse from Algebra 2, and so this is where this comes into play. Now, here, a is the length of the longer quote-unquote radius, b is the length of the shorter quote-unquote radius. Now, w is going to equal 2 pi divided by the period in Earth years. Okay, again, we're doing it relative to us, just like how an astronomical unit is in our perspective. One astronomical unit is how far we are from the sun. So we always do it in relation to where we are. Okay, and then c is the distance from the center of the ellipse to a focal point. Okay, so if you look at this picture here, so A is the length of the longer quote-unquote radius that's along the horizontal axis here. So we can see that there. B is the length of the shorter radius, so we can see that along the y-axis here. Okay, and then we see 2 pi divided by the period in Earth years is W, and C is the distance from the center of the ellipse to a focal point. So if you remember trying to find the foci, or the focus, or the foci of an ellipse in Algebra 2, that was your C value. That's what we're looking at here. Okay, so that's just a way for us to be able to apply all this information with parametric equations and be able to see its applications in something other than just a particle that's moving. We can actually say, well, we can actually use parametric equations kind of more practically if we were trying to describe planetary orbits as one example of an application.